I have drawn here the nucleus of a potassium atom. The top number, the 19, represents the atomic number. This is going to be the number of protons that are found in the nucleus. The bottom number is going to be the total atomic mass, in this case 39 units. The protons and the neutrons are going to be responsible for giving the most mass to the atom. Electrons do not have that much mass, and it's often considered negligible. So the 39 represents a total mass of 39 units. If 19 of those units are devoted to the protons, that means that there are going to be 20 units that are devoted to the neutrons. But today we're going to be taking a look at the electrons and how they're going to arrange themselves around this nucleus. In previous classes and throughout life, you may have heard that opposites attract, and that will also hold true for chemistry. So if I have 19 protons, which are all positively charged, there's going to be an equivalent match of negative charges in the case of electrons. So for every one positive proton, we should have one equally negative electron, and they're going to arrange themselves outside of this particular atom. So what I'm going to do now is draw our first orbit. So around our potassium, let me make that black so we can see it. And I shall move that right there. Now I'm going to draw a couple of electrons around the outside of this orbit. I shall place one here, and I shall place one here. So each of those red dots is an electron. If opposites attract, the same will repel each other. So each of these electrons is going to try to get as far away from the other as possible. In this first orbit, we can only fit 2 electrons. So that means we still have several more orbits to go so that we can fill it with the 19 we need. We are now going to draw our next orbit. So I shall draw that there. Alright, now in the next orbit we can actually fit 8 different electrons. So I'm going to do one here, one here, 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 5, 6, 7, and 8. Obviously I haven't drawn these to scale, and the electrons are going to be roughly the same size as opposed to these crazy formations that I've made. So at this point I have 2 in the first orbit and I have 8 in the next orbit, giving us a total of 10. That means we still have 9 more to go. So we are going to start another one of these. Go out one more. And we are going to start filling this particular shell. 1, 2, 3, 4, 5, 6, 7, and 8. So at this point we have filled the first 3 shells. In the first shell we have 2. The second shell we have 8, and the third shell we have 8. This gives us a grand total of 18. Unfortunately, that's not quite enough for what we need to do. We still have one more electron to worry about. So we are going to draw one final orbit all the way around. And I'm going to move this up here. And I'm going to actually change the color of this one. So now we have one electron in our outermost shell. This is our complete orbital diagram. And we have this one extra electron that's just floating around in the outer shell. This makes it an ideal candidate for an ionic bonding partner. If we had something, for example, chlorine, which has an atomic number of 17, it would only require one extra electron to fill its outer shell. whereas potassium would need 7. In this case, potassium will like to give up its electron to form a bond with something else that needs that electron. And we'll be exploring that more in lectures to come.